So anyway, the Bronsted acid-base reaction, we have a proton transfer. So either of these can give up a proton. What's going to give up the proton is a stronger acid, which would be water. Ammonia is typically thought of as a base. So this is our base, this is our acid. What's the driving force? Well, in the reverse direction, what's the acid, what's the base? Hydroxide's the base. This must be the acid then. So looking at this, this is going to be a weaker base, this is going to be a stronger base, weaker to stronger. So we're going from weaker to stronger. If we go from weaker to stronger, we say that there's no driving force, therefore there should be no reaction. But you know, that's not always the case. It's not always black and white in that sense, because when we have a reaction mixture like this, let's say it's a room temperature, do all the molecules move with the same energy? No, what we're going to have is we're going to have a distribution of energy. So even though it's uphill here, because ammonium and hydroxide is much higher in energy than ammonia and water, it doesn't mean that there can't be a collision where, you know, two molecules will have enough energy to collide and climb up the hill. You know, and so if we're looking at this, in other words, if we consider these balls, not all the balls will have the same energy. You know, the balls are all vibrating about like this. But to climb up this, you know, we're going from lower energy to higher energy. There could be a small fraction of molecules with enough energy to get up here. We saw this before, where there's a small fraction of molecules with enough energy to react, even though there was no driving force. It was quite a big uphill climb. Do you recall what that was? It was for water. Let's say I had 1 billion water molecules. How many water molecules can actually collide with enough energy to react to form hydronium and hydroxide? So out of 1 billion water molecules, about how many? You know? 4. About 4. 4 out of 1 billion. And so, well, how did I know that? Well, somebody went and measured that. Well, how do we know this? How do we know what it is? Well, somebody actually went and measured it. You know, how many of these can actually collide with enough energy? But it's not just energy. What else do you need in addition to energy for a successful reaction to occur? You need the right energy, and you need the right collision theory. You need the right orientation. So if you have the right energy and the right orientation, then some of these might actually make it up here. Are they going to stay up here forever? No, because ammonium and hydroxide, that's a strong base, and an acid, they're going to neutralize each other and fall back down to ammonia and water. But you know, what's going to happen is another pair are going to react and generate some more. And so what's going to result is we're going to have a constant supply of ammonium hydroxide up here, and we're going to get this kind of this going in circles where this constant supply stays pretty constant, and in fact it is going to stay constant, and the amount down here is going to stay constant, but we have this constant cycling. Do you know what we call that? Where there's no change, but there's change? Equilibrium. In fact, this is a dynamic equilibrium. Now for dynamic equilibriums, we have something called K. So let me do that over on the side here. If I have a reaction AA, where A is the coefficient and A is the reactant, first reactant, BB, this is going to go to GG plus HH. When I look at this, we're going to look at the ratio. The ratio is going to be what? It's going to be the products over the reactants. In other words, if I take a look at the products, I'm going to put the product concentration G and then raise it to the little g power, and then H raised to little h power divided by the reactants, A to little a, B to little b. And so this is what we call the ratio of the products to reactants. And this is going to be constant. because we've hit this state of dynamic equilibrium. You know, there's going to be a constant formation of ammonium and hydroxide and a constant consumption of it. And so once we hit that point where the forward rate equals the reverse rate, that is the number of balls rolling up to the top equal to the number of balls rolling down, then we're going to get a steady state or steady supply. Okay, that's that can be measured, and so when this is measured, they measure the K, which is the product to reactant ratio, a little bit more complicated than that. They come up with a number, 1.8 times 10 to the minus 5. So this is determined experimentally. 1.8 times 10 to the minus 5 tells me it's mostly product, mostly reactant, or kind of a mix of product and reaction. 1.8 times 10 to the minus 5. So one way of thinking about it is the product to reactant ratio. Is it small or big? 10 to the minus 5. Small number or big number? Or it's a small number. If it's a small number, it means it's mostly reactant. Well, that makes sense. It should be mostly reactant because there's no driving force for this, right? Other than, you know, having some molecules enough energy to collide. And so it's mostly reactant. So that's what most of the molecules are going to be down here on the left, and very few up here on the right. And so this is what we call a dynamic equilibrium. Now, when we have a dynamic equilibrium, the stoichiometry is a little different than what we normally do. If we go back to the stoichiometry chapter, in the stoichiometry chapter, we assume that, you know, all the limiting reagent reacts. Everything reacts. And so if there are any balls up here, they all roll downhill to product. And there are going to be no balls left over because the limiting reagent is completely consumed. And so when we do normal stoichiometry, we assume that the reaction goes to completion. That is, there's a 100% reaction. But in a case like this, there's a little bit of reaction. It doesn't, you know, what we're going to see is we're going to see different scenarios. Like, for example, if it's too extreme, like this, you know, the products are way up here, the reactants are way down here, then pretty much it's no reaction. You know, no balls are going to be energetic enough to get up here, or the fraction of balls is going to be so small it's insignificant, right? But as the ratio goes like this, then we're going to get more and more. And sometimes, you know, sometimes it's just a slight uphill. If it's just a slight uphill, then I'm going to expect more significant quantities of product, even though it favors the reactant. The reaction favors the reactant. And then it could be slightly downhill. If it's slightly downhill, then some can go back up. You know, it's a reversible reaction, so some can go back up the opposite way. But in our stoichiometry that we've done so far, we've just assumed it's straight shot down. That is, we're going to get 100% reaction of the limiting reactant. And so the stoichiometry is easy, you know. So in this case, if I start off with, let's say, 0.100 moles of this per liter, or in other words, 0.100 moles of ammonia, if this were a standard stoichiometry problem, I'd look, okay, which of these two is the limiting reagent? Ammonia or water? Well, typically I have lots of water, a little bit of ammonia. This would be aqueous ammonia, water being the solvent. And so typically the water is in excess. If water is in excess, what's the limiting reagent? The limiting reagent would be ammonia. And what does stoichiometry tell us? Well, stoichiometry tells us for every 0.100 moles of ammonia that reacts, I'm going to form, it's a 1-to-1 mole ratio, I'll form 0.100 moles of ammonium and 0.100 moles of hydroxide. And how much limiting reagent am I going to have left over? Nothing. It's all going to react. Well, that's assuming we have a driving force. In this case, we don't even have a driving force. And so I'd say, oh, there's no driving force, therefore there's no reaction. But is that accurate? Is there really no reaction? No, there's a tiny bit of reaction. And so this is what we call Chem 1b, what I call Chem 1b stoichiometry. Chem 1B stoichiometry is this partial reaction type stuff. In other words, we're going to do equilibrium stoichiometry. You know, this equilibrium stoichiometry deals with partial and reversible reactions, partial forward reactions, that kind of stuff. So partial reaction. Well, if there's really no reaction, then the amount of product should be 0, and K should be 0 because we have no product. If there's no product, product's 0, it's all reactants, K should be 0, but we're far away from 0. You know, that's not 0. 1.8 times 10 to the minus 5. Infinity, you know, if it was 1.8 times 10 to the minus infinity, yes, then I'd say, okay, that's close enough to 0. Okay. And so this is going to be an aside. Now, how do we do this equilibrium type stoichiometry? Well, we do it differently than we do our standard stoichiometry. So equilibrium stoichiometry, for lack. This one we have partial reaction, reversible reactions. We have to treat those differently. The way we do equilibrium stoichiometry is we set up what's called an ICE table, ICE table. We know what the final ratio should be. And so it doesn't matter what the initial ratio is. The initial ratio should change to make the final ratio. And so let's set up what we call the ICE table. So we start off with ammonia, react it with water. This is going to form ammonium and hydroxide. Okay. We know what K for this is. This is given in a table. So we just look it up in a table. It's from table or experiment or calculated using the theory. There are different ways we could calculate it from theory. We could do partial experiments, partial theory, that kind of thing. But anyway, we know what the ratio should be. That might not be the ratio we start off with. And so the ratio we start off with is called initial here. Initial. And we aren't actually going to calculate the ratio. Sometimes you'll calculate the ratio and see how far off you are. But in this case, we really don't have to start off with it, because what we're going to do is we're going to assume that we have 0.100 molar ammonia and nothing's reacted yet. This is just hypothetical because you can't turn off the collisions. I mean, when we have 0.100 molar ammonia, it's going to collide with water. We can't stop that. But what we're going to do is we're going to just do it like this. We're going to just say this 0.100 molar ammonia here. The water is in excess, and we're going to say that there's 0 molar ammonium and 0 molar hydroxide. So we're going to say nothing's collided yet. Now, when we do our stoichiometry, we're going to set it up like this. We have this ratio here, but that's not necessarily the correct ratio. We need to change this initial ratio such that we get the correct equilibrium ratio. So this E stands for equilibrium, or the end of the reaction. And C is we got to change. Well, maybe we don't have to change anything. Maybe our initial is already the correct ratio. If our initial is already the correct ratio, products to reactants, then we're safe. We don't have to do the C and the E. But if our initial is not the correct ratio, because this is the correct ratio based on what it's supposed to be here, then we gotta change it. And so here, is this the correct ratio? I have 0 product, all reactant. If I have 0 product, all reactant, that would give me a ratio of pretty much 0. And so it's not. It's got to change. And so what is the ratio? Well, in this case, what is the ratio equal to? It's going to equal the products. So it'll be the ammonium concentration to the first times the hydroxide ion concentration to the first divided by the ammonia concentration. Now water is a pure liquid. If you have pure water, does its concentration change? So for example, let's say I had some pure water and I lost a little bit of it. If you start off with some pure water and you lose a little bit of it, did it become more dilute? No, it's still pure water. If it's still pure water, even if I lost not a little, but what if I lost half of it? So if I had a gallon of water and I lost half of it, and I only have half a gallon left, is it half as concentrated? No, it's actually the same purity. So H2O is a pure liquid. Pure liquids and pure solids, the concentration doesn't really change. You know, if I have pure sugar and I consume 10 grams of it and I have 90 grams left, the concentration didn't change. So pure liquids and solids have pretty much constant concentration and are left out of this equation and are not shown in equation. And so, yeah, we need the other reactant, water, here, but I have to remember that water is a pure liquid. What is the molarity of pure water? Do you know what the molarity of pure water is? It's 55 molar. So pure water is 55 molar. So a gallon of pure water is 55 molar, or a half a gallon of pure water is 55 molar. Its concentration doesn't change. So we leave it out. And so the equation, well, everything's to the first because all the coefficients are 1. And so it's just going to be the ammonium times the hydroxide divided by the ammonia. Well, that ratio should be 1.8 times 10 to the minus 5, and if it isn't, there's going to be a change. Now here, there's got to be a change. In this case, what we're going to see is we're going to see some of this react. How much? I don't know yet, so we're going to call it X, minus X molar. Some of it reacts. If I lose minus X, I'm going to gain plus X molar here and plus X molar here because this is a 1-to-1-to-1 ratio. And pure water, that doesn't change, so I'll just ignore that. And so at the end of this, once I hit the correct ratio, I'm going to have 0.100 minus X. Over here, I'm going to have X, and here I'll have X. Molar and X molar. Yeah. So all I need to know is what my X is. How can I figure out what my X is? You know, I know a little bit of this has to react. How much? And so I have to solve for X. Well, how can I solve for X? Well, I need some more. You know, I have 0 equations and 1 unknown. If I have 0 equations, I at least need 1 equation, 1 unknown. But what's the equation? Well, the way I'm going to solve for X is by substitution. And so here, we're going to substitute it. And so K is going to equal the ammonium concentration. Ammonium concentration is X, times the hydroxide concentration, which is X first, divided by the ammonia concentration. The ammonia concentration is 0.100 minus X. Okay, and whatever this change is, it's going to have to impact the initial such that the ratio comes out right. It's got to come out to 1.8 times 10 to the minus 5. And so now we can solve for X. We have an equation. So it's going to be X squared is equal to 1.8 times 10 to the minus 5 times 0.1 will give us 1.8 times 10 to the minus 6. And then this is going to be minus X times that. So it's minus 1.8 times 10 to the minus 5 X. Okay, then we're going to get this into quadratic form. X squared plus 1.8 times 10 to the minus 5 minus 1.8 times 10 to the minus 6 is equal to 0. Okay, this is what I call the Chem 1B stoichiometry. Chem 1B stoichiometry, it helps if you have a calculator that solves quadratics. And so this is why I made the recommendation for that particular calculator. Because if you have a calculator that solves quadratics, you can save a lot of time. in your homework. Otherwise, do you guys remember the quadratic equation? Quadratic equation, x is equal to minus v plus or minus square root something like this. 2a, a squared. 2a. Is that right? Yeah. Okay, so you have that option. Or if you have a calculator that solves quadratic, then you could just plug it in. And so what is a? A is 1, right? 1x squared. What is b? B is 1.8 times 10 to the minus 5 in x. We'll just plug it in. 1.8 times 10 to the minus 5. You can see I already did this. What is c? Negative 1.8. Negative 1.8 times 10 to the minus 6. And so the Casio, you just plug in A, B, C, and you'll get the two roots. The first one, negative, we have to pick one of these. And so is it possible to have a negative concentration of hydroxide or ammonium? No, it's impossible. So negative, we're going to get rid of that. And so x is equal to negative 1.00135, impossible. Negative concentrations are impossible. So we have to go with a positive. It's going to be positive 0.001332. And so this allowed us to solve for x here. And so the ammonium concentration, after this is reacted, is going to come out to 0.00132 molar. Actually, I'm not allowed that many digits. 0.00132 molar. The hydroxide and the ammonium. And then the ammonia is 0.100 minus 0.00132. Now, this was given here, 0.100. That's because 0.100 is something you can make easily by solution dilution. And 2, I like 100 because of this. For every 100, how many did we lose? So for every 100, let's move this 3 over. We'll move this 3 over. We lost 1.3. If we lost 1.3, that we call that the percent reaction. And so if I have this as 100 and this is 1.3, then I have 1.3% reaction. 1.3% reaction is far from 100% reaction. In normal stoichiometry, we do 100% reaction, limiting reactant. But it's also far from 0. There was a little bit of reaction, and it definitely was not no reaction. Just had a little bit of reaction. And so we're going to be left with 0.09886, etc. 0.09886. We'll just leave it at that. Molar ammonia. All right, so this is what we do. We see that ammonia does this. Weak bases and strong bases, do they ionize in water, or do they, what's that other word? Bases, do they ionize in water, or do they? Well, I know acids. Acids can either ionize in water, or they can, starts with an H. Hydrolyze. Can bases ionize in water? True or false? Bases can ionize in water. Well, I shouldn't say that. No, what happens with bases is they don't ionize. Bases hydrolyze. That is, they react with water, split the water apart. So bases hydrolyze. Whether they're weak or strong, they're going to hydrolyze water. And so if I were to ask you, what is the pH of ammonia, you'd go, well, ammonia, where's the H plus concentration? I need the H plus concentration to do pH, but ammonia is not an acid. Ammonia is a base. And so how can you get pH for a base solution? Well, you get the pH for a base solution because bases hydrolyze water to produce hydroxide. And so one of the things we can get from this is the pH, not directly, because first we'll have to go to pOH. What is the pOH? The pOH would be the negative log of the hydroxide. The negative log of the hydroxide is 0.001332. And so let's see what that comes out to here. The log. That comes out to 2.875. I'm only allowed 2 sig figs. In power functions, it's after the decimal, so both of those numbers show 2 sig figs. If the pOH is 2.875, well, I'm not interested in pOH. I'm interested in the pH. What is the pH equal to? The pH is going to be 14.00 minus 2.875. Oops. 11.12. 11.124. That's my pH. 11.124. 11.124 makes ammonia solution basic, acidic, or neutral. Acidic? Or actually basic. High pHs are basic, low pHs are acidic. And so that's a kind of a high pH, therefore it's basic. At least say it moderately basic. You know, strongly basic would have a pH closer to what? 14. And so this is moderately basic. pH is 11.124, and we got the pH by hydrolyzing water, creating hydroxide, which gave us a pOH, which then gave us a pH. So we can use this. This ice calculation you aren't going to have to do. And so this we'll call an aside. I just wanted to show you an example calculation. That's it. Since I'm skipping most of the chapter involves this type of calculation. So this is just a side calculation. So is ammonia used for anything else other than making a solution basic? What can ammonia be used for? Ammonia could be used to make water basic. What else could it be used for? This is a Bronsted acid-base reaction. It could be used to neutralize acids. What else could ammonia be used for? Could be used as a reducing agent or oxidizing agent in redox reactions. Reducing or oxidizing agent? Or maybe both or neither? In other words, tell me the chemical properties of ammonia. Depends on how in depth you want to get. What were the chemical properties that we dealt with? Metathesis. What else? Acid base. So we did Bronsted acid-base. So ammonia is a base. It reacts with acids. Ammonia could also be an acid. It's amphoteric, but it's a very, very bad acid. I mean, it's not very strong at all. It's extremely weak. It's an acid. So most people think of ammonia as a base. So how does it rank amongst the bases? It's here. Do you see? It's here. Stronger base than this one. What's this one called? See that? What's this base called? HPO4 2 minus. Biphosphate? You could call it biphosphate, but if you called HPO4 2 minus biphosphate, then what would you call H2PO4 minus? Biphosphate? If that were the case, then yes, call this one biphosphate and the other biphosphate. But that's not the case, so we're going to have to use a different naming system. And what's the naming system we're going to have to use to differentiate these two phosphates? The H2PO4 and the HPO4.
HPO4 is going to be hydrogen phosphate.
All right, then what would H2PO4?
Hydrogen phosphate.
Okay, yeah. Oh, close, very close. We're going to call HPO4 not hydrogen phosphate. We're going to call it, just to make it extra clear, because if somebody says I have some hydrogen phosphate, you don't know what they're talking about. Are you talking about 1, 2, or 3? If you're talking about 3, we call it phosphoric acid, and you should be calling it phosphoric acid, like here. Oops, did they forget phosphoric acid? Oh, here it is. But if you have 2, then we're going to call it dihydrogen phosphate. 3, we don't call it trihydrogen phosphate, because that should more properly be called phosphoric acid. And then if we have 1, we're going to call it monohydrogen phosphate. 1 is monohydrogen phosphate. All right, so you want to start reviewing for the final. And when you start reviewing for the final, you got to review all this nomenclature stuff because you're going to see it in the final. So, in other words, ammonia is a stronger base than monohydrogen phosphate, but a weaker base than this. Cm minus is called cyanide. And then we have stronger bases over here. But ammonia is amphoteric. What does amphoteric mean? Yeah, and so most people think of ammonia as a base, and they'd be correct, you know, because ammonia as an acid, well, ammonia is a weaker acid than this. What's this called? We call this hydrogen sulfide, but we have to be careful because what is this called? H2S. That historically has been called hydrogen sulfide. You might want to call this dihydrogen monosulfide or dihydrogen sulfide, but it's not. This has historically been known as hydrogen sulfide. So if H2S is called hydrogen sulfide or hydrosulfuric acid, then HS minus should be called hydrogen sulfide ion. And so here, ion is mandatory. Whereas over here, it's not. Like sulfide, everybody knows sulfide's got to be an ion, so you don't need to put the word ion there. Or hydroxide, everybody knows hydroxide's an ion. And so hydroxide ion is redundant, but hydrogen sulfide ion is not. But anyway, ammonia is a weaker acid than hydrogen sulfide ion, but a stronger acid than. But do you think of hydroxide as being a very good acid? No. In fact, ammonia is a weaker acid than water. And so these we really don't really consider as being significant acids because they're even weaker than water. Well, anyway, so as far as acid base goes, ammonia is a pretty decent base. As far as redox goes, is ammonia electron rich or electron poor? Electron rich. What's the oxidation state of nitrogen in ammonia? -3. Good. So as far as redox goes, ammonia is pretty electron rich, a reducer. What about metathesis? Can ammonia, well, metathesis, what's another way of saying metathesis? Metathesis is favorable ion combinations. Is ammonia an ion? No, it's not. And so initially you would think ammonia doesn't participate in metathesis reactions, right? Because ammonia is not an ion. And metathesis deals with ion combinations, so if ammonia is not an ion, then it shouldn't be participating in ion combinations. However, what happens is this. When you put ammonia in water, ammonia hydrolyzes water to form ammonium ions and hydroxide ions. Although the concentration is small, only 1.3% of this reacts. These ions are able to participate in metathesis reactions. And so let me tell you one application for aqueous ammonia. One of the chemical properties of ammonia, or aqueous ammonia, is aqueous ammonia can precipitate insoluble hydroxides. And so let's look at an application of that. And the application would be, let's say I had some, can you name an ion that likes hydroxide? I can. Magnesium ions. Magnesium ions like hydroxide. So if magnesium and hydroxide react, what forms? Magnesium hydroxide. Magnesium hydroxide, is it soluble or insoluble? Insoluble? Yeah, milk of magnesia. This is why it doesn't kill you right off. It's because it's pretty insoluble. Then we'll need this, 2 hydroxides. So this is the driving force of precipitation. And so these ions like each other. And so one application of aqueous ammonia is to precipitate out insoluble hydroxides. And so the overall reaction looks like this. Overall reaction is, let's take some magnesium chloride, for example. Magnesium chloride that has magnesium ions. And then we're going to react it with ammonia and water. So if I take my magnesium and react it with like 2 ammonias and 2 waters, then I'll form magnesium hydroxide, solid, plus 2 ammonium chloride. And so although this doesn't look like a metathesis reaction, this is a metathesis reaction. Metathesis should be favorable ion combinations, but I don't see the ions. You don't see the ions because the ions are produced from ammonia and water. And so ammonia and water are going to react. This is about 1% reaction. And it's going to form some hydroxide, and those hydroxides can react. The driving force here is the precipitation of magnesium hydroxide. This is the overall reaction. But you go, well, ammonia and water, they combine to form ammonium and hydroxide. So isn't really the hydroxide that's reacting? Shouldn't we show this as magnesium ions plus 2 hydroxides like we did over there? And the reason we don't show it like that is this. This is the overall reaction. So let's say if you ate sugar or you eat food. If you eat food, what happened? If you eat food, then you have this metabolic cycle that digests the food and extracts the energy out of that, right? One of the things in the metabolic cycle is like this. This is part of it. This is the citric acid cycle. You look at the citric acid cycle, what goes into the citric acid cycle? Pyruvate. Did you eat pyruvate or did you eat food? You ate food, and that food was converted into pyruvate, whatever, and then it goes through here, and then it follows along this whole process. A whole bunch of reactions occur, right? And so the point of this is this. A lot of people think that this is wrong. This is wrong because this is metathesis, and there should be hydroxides here, and the hydroxides are reacting with magnesium, right? Not the ammonia, not the water. But the situation is you didn't eat the hydroxide. You just ate the ammonia and water and magnesium chloride. But you didn't eat hydroxide, did you? Did you go to the store and buy? In other words, we know that pyruvate's going to go in here, but did you go to the store and buy pyruvate? Maybe you did, but you didn't have to because it's part of the whole cycle. And so what we want to do is we just want to show what goes in. What goes in is this. What comes out is this. You know, what goes in there is food, and then energy comes out from that. And so basically boils down to this. Let me give you a little hint here. When we have ammonia and water, that's going to form 2 ammonium hydroxides. But we don't show it as ammonium hydroxide. This is like saying, okay, food goes in, but rather than writing food, I'm just going to write pyruvate. Pyruvate for everything. You know, it's pyruvate. Pyruvate's there at the beginning, so it's got to be pyruvate, right? But you didn't eat pyruvate. If you go to the store to try to buy ammonium hydroxide, you might feel ripped off. If you go to the store to buy a bottle of ammonium hydroxide, they're going to give you a bottle of ammonium hydroxide. But it's only going to contain 1.3% ammonium hydroxide, 98% ammonia. And you go, I want to return this. I want to return this because I asked for ammonium hydroxide. You gave me ammonia and water. Okay, they take it back and they give you a new bottle, but the new bottle is going to contain 98%, 99% ammonia and 1% ammonium hydroxide. And so it's because of the equilibrium balance here. So when you go buy this, you aren't buying ammonium hydroxide. Is ammonium hydroxide stable? No. What you're buying is ammonia and water. So this is like, okay, I'm going to eat food. I eat food. You know, you go, I want to return this food. I want pyruvate. You know, I want. You aren't going to get it. You're going to get this. And so this is the way we're going to write this reaction. And so I skipped this. I skipped this because I made the slides for Chem 1A. But I'm going to come back to it now. Do you remember this, the chemical reactions? I don't know, when did I talk about metathesis? like near the beginning of the semester. Do you guys remember these PowerPoints? Yeah? Okay. So we talked about metathesis here in the PowerPoint. And then I skipped this. Weak electrolyte molecular compounds might participate. Example, ammonia and ammonia-like compounds can participate in metathesis reactions. I skipped it at that time because I didn't want to talk about this. And so I skipped this slide, slide number 23. Magnesium nitrate and aqueous ammonia. That's a metathesis reaction. What forms? So can you write the CE and the driving force, the IE and the NIE for this now? Can you do that? The CE, the IE, and the NIE plus driving force for this reaction.